here we go. I'm looking, I'm evaluating, and I'm saying it's time. It's time to make things general. One more dimension. Let's start to push it now. Just in case you want to work on this homework this weekend. I think that's kind of where I want to be. Okay? I feel like those quick checks we did and the discussion we did ought to give you a chance that you can do an attempt at that 16.5 homework now. And we'll see where it goes, okay? On Tuesday next week, I'll take whatever questions you have, okay? Really for the first 5 sections of the chapter, well, first 6 if we work on this. Monday next week. Monday, Wednesday. Please don't hesitate to come by office hours either. These last 2 weeks I know are crunch time for you. I know you're working on problems outside of class. Stop by, okay? The rest of this week, next week, and I'd be happy to help you. If I don't know, sometimes I have to do some homework and get back to you, and that's happening also. All right, so 16.6, we're going to talk about surface area. Again, why? Why do we want to do this? Because really what happens is, right? It's not surface area, it's surface integrals is where I'm going with this eventually. Because we have line integrals, right? So this kind of thing. And we're going to kind of up it a dimension. So that when we do Green's theorem, right, we're going to up it a dimension. What did I put here for you guys? What do you guys put here, a D? Yeah. Okay. So again, this is the game we're playing, is we're trying to up things a dimension. Your book mentions some other parallels, which are kind of nice. Let me jump to that now. Right up here, before they even started any of the, parallel concepts, right? Between curves and surfaces, right? So they say, well, when you have a curve, you can talk about its arc length. Right? We like to parameterize by arc length. So now in this higher dimensional setting, we're going to parameterize by surface area. Line integrals and surface integrals. Oh yeah, so that's the key. 1 parameter or 2 parameters. Okay? When we parameterize by surface area, there's going to be 2 parameters. By the way, when you have 1 parameter, we've been usually using, the letter T. When we use 2 parameters, our book chooses to use U and V. That's not that uncommon. I've seen S and T. I've seen U and V. Bless you. So that's kind of weird. Remember we just had a U on the previous page? It was a function. No, these U's are parameters. Just they're taking the same spot place as T. Okay, so let's take a little peek at what's going on here. How do you parameterize a surface? Well, if you look at that R, perhaps that occurred to you at some point that you might be able to do this. Maybe it didn't, I don't know. But think about Calc 3 for a minute. What did we do? Let me go back through it. So we started in chapters 13 and 14, right? And what we did was we talked about R of t, R prime of t. What's another name for R prime of t? V of t. Right? And then if you divide r prime of t by its length, you get that capital T. We did all this kind of stuff, right, in chapter 13 and 14. And then in chapter 15, what did we do? In chapter 15, we were dealing with functions, and really maybe this is 14 and 15. We were dealing with functions of x and y, right? So now, here we are at the end of chapter 16, and we're kind of putting these ideas together. Yeah, when I write r, it's going to be a vector-valued function, right? It's going to be a point somewhere in space, you might say, or a vector, either one. But what you have now is you have r is a function of u and v, not just a function of t. That's kind of cool. 2 parameters. So algebraically, I could write it on the board, and there's nothing more complicated about what I just did. But geometrically, and your book can do this, they can show you some really cool things. Bless you. So here's their first picture. See that surface? When we say that r depends on u and v, that's a vector-valued function. There are 3 scalar-valued functions here. The x-coordinate depends on both u and v, the y-coordinate depends on both u and v, and the z-coordinate depends on both u and v. Have I ever done this before? I don't know. You guys tell me. Does this look familiar if I write it in 1 dimension? R of t equals, didn't we write this like the first day of class maybe? What do you think? Does that make sense? You can get the 3 coordinates. Maybe it's t squared, and 4 or something. I mean, I don't know what it is. Well, now we're going to have functions of 2 variables. And so what they do, this is really cool. See this? The UV plane, that's your inputs. And so they're showing you, I think this is awesome. You can take that point and you can move it somewhere, and whatever input you are in puts you somewhere on the surface. Do you see that? That's what we mean by parameterization by 2 variables. Hey, once I do that, could I parameterize something by 3 variables? Move a point through space and then, right? I mean, you could do this. So this is kind of like just a level of abstraction we've added, but it's really cool to look at. Okay, next. We have, in Cartesian coordinates, we have something, remember we defined this, we called them cylinders? And so what we did was we said, well, x and y, I know how to get those. And z, I'm just going to say, let's take all the z's. So that would be an infinite cylinder, right? Well, now what we're going to do is we're going to just instead parameterize. Let's take a look at what the picture looks like. So you'll notice that v is actually representing what here? What is v representing? Where's the only place v shows up in that equation? It's the z-coordinate. We've done that before. Sometimes I'll let x equal t, and then y is t squared. That would be a parabola, y equals x squared, right? So they're going to let z be v. And then they used u to represent where you are on the circle, right? It's almost like the polar coordinate idea here, right? So let's see what happens here. Well, same thing. I can change. So I'll stay right at pi here. No, let's not. I want to get where you can see it. Let's get a good value of theta. There, pi over 2. Now you can see the green line, right? Right on the y-axis. You guys see it? And then I can go up and down, right? So that's the z, and here's the y. It's really kind of cool. Oh, what's this? Oh, that's a, right? So in general, a cylinder would be a cosine u, a sine u, and v. So they're basically trying to give you some simple shapes that we can parameterize with 2 variables very nicely. Here's another one. Oh, what's this? A cone. How do you do a cone? Well, you do it kind of like, actually, this would have been helpful on your exam, right? Question 6.
Yes.
Because what it came down to, I think, was could you understand that really what's here is the slope of the line, right? In say the YZ plane alone. Here, let me do the same game. Let me get that green line so it's right on the y-axis. So I'll go to pi over 2. There. Now I'm right on the... So what I really want is the slope of that line. And again, they say the slope is AV over H. So if I change A, it's going to change the slope. There's a more skinny cone and there's a wider cone, right? So that's the kind of thing we were doing. By the way, I'll post the answers to the exam today, so you guys can take a look. I have all these things worked out nicely. That last question was tough. They can do a sphere. How do we do it? Well, look, U is going to take the place of phi, V is going to take the place of theta, and then we know the equations, right? So this is easy to do because we already have coordinates. We can turn them into parameters. And what's really cool now is every point on the sphere is identified by some point on the rectangle, right? So where are we? Northeast Ohio is right about there. Yeah? Who's to say? I don't know, but that's the idea. Okay. Find parametric descriptions for the following surfaces. A plane, 3x minus 2y plus z equals 2. I mean, what do you do? Let's take a look. Oh, well, they say let u equal x and let v equal y. Let's take that hint. Let's take that hint and see what happens now. All right? So if I do that, so I would write 3u minus 2v, right? This is example 1. Part A. Okay. Well, 3u minus 2v. Now we still have this plus z, right? Equals 2. Why?
Because you can just switch the 3x minus 2y over to the other side. It comes to
Sure.
plus.
So z is equal to what? 2 minus 3u plus 2v or something like that?
Yeah.
Yeah. So there's z, right? And so now I guess I've done it, right? I can say that r of u comma v is equal to, well, okay, here we go. We said x is u, we said y is v, and now z is given by 2 minus 3u plus 2v. There's a parameterization of the plane. And again, I'd have a UV rectangle, and I could get a point on the plane by selecting a point on the rectangle. Are you with me? What's the 0, 0 correspond to? I guess 0, 0, 2, right? This plane goes through 0, 0, 2. And this is an important idea because just like it was helpful for us to work with r of t, we're going to find we can do an awful lot by working with r of u and v. So where do we go now? Well, we want to talk about surface integrals here in a minute. And so the game, oh, did I do the quick check? I think I skipped it. No, we should do that real quick. I don't want to skip these too much. Quick check 3. Actually, I skipped a couple. Oh, that's okay. Let's do quick check 3. Describe this surface for 0 less than or equal to u less than or equal to pi over 2 and 0. Hey, what does that look an awful lot like, guys? Spherical coordinates. This is going to be a portion of a sphere. a portion of a sphere of radius 4, right? Because that's like my R. Well, actually, it's my rho, right? Rho is 4 here. And then the U and V are the phi and theta. I guess what you might have to look at is the U and V, does that going to give you a portion? Notice it said a quarter sphere. Why does it say a quarter sphere? Because normally, this is U's taking the place of theta, right? And so if you only go from 0 to pi over 2, you're going to get a quarter of a sphere. That's kind of interesting. Okay. So they're starting to explain here how to do surface area. And there's lots of cool pictures I can go to, but I almost think it might be better for me to give you kind of my own little presentation. So I'm going to do that. So we need the following. To compute surface area, we will use R of U comma V, which is X of U comma V, Y of UV, and Z of UV. And I hope that I gave you enough examples that you have a vague notion of what I'm talking about. That's what I hope just happened. That was the point of the first few minutes of this lecture, and pictures. And I want to use that. How? Here's the first thing I'm going to do. I'm going to define N of UV to equal okay, do I want to call it R, or your book calls it little t. I'm going to do this anyways. RU of UV cross RV of UV. Right? RV. I just saw those in Indiana. The RV Superstore. Right by the highway. Anyways, what we have here, okay? Well, this is what kind of vector? Normal. Normal to what?
The tangent of the U component, the tangent of the V component.
Yeah, that's what we're looking at here. These are, your book calls these things little t. They write little t for tangent vector. Our book uses little t. But all they are, guys, are partial derivatives in the u direction and in the v direction. So, boy, do I dare try to be artistic? Yeah, we're going to try. You see that? That's a surface. Ooh. Here's a point on the surface. Does it look like a point on the surface? Okay. So you could have, boy, can I draw it? I don't know. Like a plane tangent to that. And see, now's when I'm losing it. Now's when I'm losing anything resembling 3 dimensions, right? But if you could somehow pick 2 vectors such that those vectors corresponded to rate of change in the u direction and the v direction, that's what we want. U and v, by the way, these 2 directions aren't necessarily orthogonal, aren't necessarily perpendicular here, but they are down here, right? This is just good old graph paper. And it all seems mysterious. I understand that. But maybe this is the next place to go. Oh yeah, I actually mentioned this today. Kind of. Let's remember something. recall that, how do I say this? The length of the normal vector equals, how about I say, the area of a parallelogram. Does anyone recall that? I wish it were, yeah. It's supposed to be in count 2. So let me say it again. What I mean by that is, at some point, you guys learned cross product. Yeah? How does it work? You have 2 vectors. You compute the cross product. What does it equal? Isn't it a third vector? Right? How long is that third vector? Well, it turns out that if you take these 2 and you make a parallelogram, the area of that parallelogram is the same as the length of the normal vector. The other fact about the normal vector is that it's perpendicular to. So remember when you guys were, I was going over earlier today, I said, hey, we can find determinant, right? What is it? I said, it's a number that goes with a matrix. Well, what does it mean? Well, it has something to do with this idea, this area of the parallelogram kind of thing. How could it be negative? Well, that's why I said it has something to do with it, okay? Anyways, if I take the length of the normal vector, it's the area of the parallelogram, right? So in particular, it's almost like if these really are the 2 vectors, see that? You could get that area of that black parallelogram. Now, if the vectors are small, and if I add up all these little areas, I get an approximation to the surface area. Riemann sum, you've seen the game before. Yep. Let's take 2 minutes to look at the book's pictures, guys. Because we can. This is so cool to have a book like this. Here we go. Let's see. Here we go. Ah, yes. This little guy, fine. We can subdivide into intervals. Oh, there's the green parallelogram. See, they're using TU and TV. And they say N is TU cross TV. Fine, whatever. I think people watch too much TV, so we'll go with ours. So now we're here, right? And it's a Riemann sum. I really wanted pictures, not formulas. Well, okay. If they're going to do that, I'm going to write my own formula in a second here. I want a picture. Ah, we have a picture. Okay, play. Find, no, that's boring. We already did that picture. That's not what I want. Oh, they're just kind of showing you how the normal vector really does always point away from the surface. Okay, I'm sure you believe that. I thought there was a better. It's okay. It's okay. Where are they?
It makes you feel like there aren't really many pictures in the book.
No, there's a lot. Here we go. Here we go. Okay. So this is kind of interesting. What's varying here? V, right? So for any particular V, I'm moving, for any particular A, as V moves, you can kind of see the normal vector moving here. Definitely this normal vector seems to be important, huh? All right, let's write it down.
I think that picture you might be looking for is 15, or is that 16.46?
Yeah, did I miss it?
Maybe it was right after quick check 3.
Wow, there's so many. Let's move on. So the area of the parallelogram, okay, it's the double integral, well, in general. Let's just say, how do I do this? Riemann sum idea. I think that's honestly enough for us, for our purposes, to say that the area is going to be the double integral over R of the length of the normal vector of UV. du dv, let's say. Okay, so this would be surface area. Hey, by the way, what was the one-dimensional analog of surface area? Let's be more specific. Line integrals work as surface integrals, I agree. But just surface area formula is what I have here. So you can have the area of a surface in space. What if you're down, back to Green's theorem, we have a line integral. What can we say about a line integral, about a curve? The length of the curve. Yeah, it's called the arc length, right? I want to keep drawing that parallel. I think that's a really important point here. Arc length. You must be able to get arc length by a single integral. Isn't that true? Do you remember, I'm going to write dt here. Do you remember what it is that you have to integrate to get the arc length? So that's interesting. I'm going to write that as a dx integral. You're right. I think that was a Calc 2 way of doing it. And then we changed f prime of x to, well, dy dx squared. Yeah, I love this computation. It's like I'm really flying through it. And then you use the chain rule, and what you might have done also in Calc 2 if they were really good is they might have done something like this. No. Okay. This is parametric. But do you see how I could get from here to here, kind of, with the chain rule? The dx squared is there, the dy squared is here, and the dt squared is here. Right? As a matter of fact, let me do one more move. I claim that this is almost r of t. Not really. It's not r of t. Well, wait a minute. It's almost r prime of t. Wait a minute. What is r prime of t? Hold on. I'm going too fast. What's r of t? 2 dimensions, guys. Oh, yeah. So if I say r prime of t would be x prime of t, y prime of t, right? Right? So what is this? It's the square root of this squared plus that squared, right? So isn't that what it is? I remember someone teaching me this recently in Calc 3. Arc length. What do? I integrate the speed, right? And that's why we parameterize by arc length, because that was kind of your unit speed, right? Why bring that up now? Well, A, we have a final coming up. But B, well, no, it's more than we can. It's because there's a parallel, right? I don't integrate the absolute value of r prime. I'm integrating the absolute value of the normal vector. But that's kind of cool. Because if you think about it, r prime was giving you this length of this arc. And somehow the length of the normal vectors being the area of the parallelogram you could start to see why integrating it would actually give you the surface area. Is this a rigorous argument? No. I went through 3 pages of fairly rigorous stuff and just showed you the pictures, right? But that's what you want. No, I mean, that's how we learn. That's how we learn. Okay?
It doesn't make sense though.
What doesn't?
How is speed analogous to a normal vector?
It's not.
With the arc length, you're taking distance times time, or speed times time, which is distance.
Yeah. Here, I really am adding up lots of these little black parallelograms, as opposed to adding up lots of little moves in one direction. So there is a difference there. There is a difference. I see what you're saying. You say, that doesn't make sense. They're not, the generalization doesn't fly. I get that. But you almost have to see one more thing here for it to fly. And that's this. Some of you, believe it or not, well, most of you wouldn't believe this, but there are actually some people in here that are still working on section 16.2, which is all about line integrals. I'm just kidding. Most of you are still working on this. So, don't feel, am I the only one? No, really. So, line integrals, what do they look like? They look like this. Curve, and then what do you put over here? D what? What does S stand for? Boy, I keep coming back to that. Okay. So there's going to be something here, ds. But when you actually want to compute it, you change it to a regular old integral dt, right? Or there's other ways. We've shown you a lot of stuff, okay? So, I guess what we're going to do now is we're going to do surface integrals. And just like when you guys may have noticed that the square root of r prime of t, the absolute value of r prime of t shows up here, right? When you change from arc length, you have to put this, you might call this the arc length element. It shows up. That square root of x squared plus y squared shows up when you do line integrals. Well, I guess my point is, what's going to show up when we do surface integrals is this, the absolute value or the length of the normal vector. So now it's time to look at a formula or two in the book. Here? Sure. I want an example. Quick check is okay, but let's do an example. There we go. Find the average temperature on a sphere. The temperature on the surface of a sphere varies with latitude according to this function. Aha. Find the average temperature over the sphere. Solution. By the way, the fact that they say average temperature means that they're probably going to do what? Divide by the total surface area of a sphere. How do we do that? Are we going to do it with a double integral, or are we going to use geometry? Okay, geometry, 4 pi r squared, right? Okay, so let's see what they do. Yeah, see, they divided by 4 pi a squared. Okay, fine, so they'll do that at the end. But in the meantime, what are they going to do? Okay, notice the formula. Double integral, right? But here's the key. Just like in line integrals, we have to throw in an r prime of t to change the parameter, right? To something we want to turn a line integral into a regular integral. So we can put, t equals 0 and t equals 3 here, or whatever the, if you have 0 less than or equal to t less than or equal to 3. Same thing for them, but they're going to have a double integral with u and v. Let's see what happens. They're saying u is between 0 and pi. Why are they saying u's between 0 and pi? Oh, that must take the place of phi. Yeah, u is phi, and v is theta, right? And notice what they had to throw in, guys. See that? That gets thrown in, that a squared sine of u. This is huge. You have to compute the normal vector and throw it in to change to parametric. Okay? So, back to our parallels, so that we understand what's really happening here. Okay? Wow, there were a lot. I think it's back on this page. Yep. We have line integrals. And I said my job today is to try and show you the parallel. The parallel is going to be a surface integral. So it will be a surface integral. And this is where S is parametrized by some function, r of u v, and then we need the normal vector of u v, which you get by cross product and absolute value. So that's something else to write down, is that we're going to need that. Okay. So now the question is, I'm going to close by trying 28, at least setting it up. If we have to finish it next time, we will. So 28 says, compute this surface integral. Double integral over S, f of x, y, z, d, and notice they put a big S. That's your key. You have a surface integral here, okay? Using a parametric description of the surface. So we say f of x, y, z is equal to y. Okay. Fine. And then the cylinder that we're talking about, S, is the cylinder, they say, described by x squared plus y squared equals 9, and z is between 0 and 3. Okay. Well, I'm going to do it. I'm going to do double integral. Hey, let's put a y here for now. And now, when I start to do this, I know I'm going to want the absolute value of the normal vector. So I'll have to compute that. And then I can do, my du dv or something like that. Okay. I'll just write, well, okay, so let's see if we can make a little bit of progress here. One of the reasons that they had me in the quick checks show you some of these pictures that occur commonly is because coming up with the parameterization, there's lots of ways of doing it, but there's some that are easier than others, right? Do you remember what the trick was? We're going to let v be the same as z, right? So v is going to be z. And then what about u? U is going to be kind of theta. Does that make sense? Because if I'm thinking polar coordinates, what do I know about r? R is always equal to what? The radius is 3, right? So let's see if this makes sense to you or not. The parameterization of S we can describe in the following way. R of uv is equal to 3 cosine theta Not theta. What am I writing? U. 3 sine U. And then I'll put V for my Z. And yeah, I'll pick it up here next time, guys, but at least that gives you kind of a starting point. Some of the homework is just setting up parameterizations, but we'll actually do a problem or two next time also.